Welcome to this quick tour through Mechanomy's Model Composer. This was written about 3 years ago and made it to about alpha level status, but it provides a quick introduction to engineers to the idea and power of the Modelica modeling language and how you can use Modelica to model real physical systems. So first off, here on the home page are some example models that are pretty easy to just jump into. This one is the simplest, modeling a bouncing ball, and it does so using the coefficient of restitution and acceleration due to gravity. The ball will start from a height of 111 meters, so here's another variable describing that. And we're primarily interested in the ball's velocity. When the ball hits the ground, well, we need to apply the coefficient of restitution to the ball's velocity right preceding the impact, and we do that down here in this equation section. We're going to run the experiment, the simulation, from 0 to 110 seconds, and after that, after we run the experiment, we're going to generate a bunch of plots to just show how the ball bounces. So first off, when the simulation completes, we're given a results object with variables as a time series, so the height, the velocity, whether it's impact, and we can download that. And then down here we have the plots that we designed here. The primary one is of course the height versus time, and so here we see the ball starting at 111 and then subsequently impacting the ground each time, rising to a lower height because of the energy loss of the coefficient of restitution. We can also plot the velocity, whether it's in impact and any other calculated results. So this was a pretty easy, simple model. If we go to one that's a little bit more complex, say this caterpillar excavator, we get to see the greater power of Modelica, which is really summed up in its standard library. The Modelica standard library is all these statements that begin with Modelica, and within it, it has a variety of physical domains that are modeled. Electricity, thermodynamics, fluids, and of course mechanics. And in mechanics, we have the idea of rigid bodies, revolute joints, force elements, damping elements, friction elements, gear transmissions, other physically recognizable components that are common or commonly encountered as a hardware engineer. So in this model, what we're doing is we're modeling just the excavator arm of this very small cat excavator. And so what we have is a revolute joint here at the base. We have one large rigid body. We have a second revolute joint and a rigid body, and then we have a bucket. We're not going to model the hydraulics or the environment that it's interacting with. Hydraulics are doable, the environment is very much harder. But if we come back to the editor, here we have the geometry taken from an image of the excavator. So these are pixel values that we're converting into meters. We have a nominal damping applied to the different joints. As I said before, we've got the boom, the stick, and the bucket, 3 rigid bodies, and then 3 revolute joints between them, allowing them to move. We also introduce damping and some friction. So these are the things we have to play with. These are the variables that essentially we want to work with and that we eventually want to solve. And we need to create equations between these, or relationships between these elements, and we do that through these connect statements. And these connect statements can be viewed as aligning up 2 parts of an interface. So here we align one element, the frame connector of a revolute joint, to the frame connector of the boom arm, and so on. We proceed from the ground all the way out to the bucket, and then we return and put some dampers on those various joints as we intended to. If we do things correctly, this equation section will have the same number of equations as variables were introduced up here. And that's key to solving the overall system. It will absolutely complain if you do not have those aligned. The experiment itself is going to run, the simulation is going to run from a start time of 0 to through a single second. And in this, because of how we modeled it, the arm is just simply going to fall from the initial position downward due to the force of gravity. And the force of gravity is implicit in this world object here. And once the results complete, then we're going to analyze by throwing up 3 plots of the arm motion. And so right now, we've just sent off the model text up to a server. The server is simulating that in Open Modelica, and then the server will send the results back to our client session here. Again, we've got a CSV of the results, except this time we've got many, many more results. The great power of Modelica is that it can do complex things. There are lots of equations that are behind the scenes that are necessary, frankly, to be able to model physically realistic systems. This plot on the left is the most obvious, which is simply here's the boom, here's the stick, here's the bucket at the initial configuration, and then as time progresses, it's all going to fall downward under the force of gravity. And we can see that in the joint angles on this graph, again, versus time, how things move. And then here on the far right, we're looking at the internal forces of the bearing between the, what's W and L? Yeah, the internal forces of the bearing, of this bearing here, between the world and then the boom. And we see them in the canonical directions of X, Y, and Z. And this is just the start of the analysis, because what we're able to see here is that the forces are strong functions of the joint angle. And in an excavator, the bearings don't ever make a full revolution, or many of the bearings don't make full revolutions. And what that means is that the bearing should not be designed expecting continuous revolution. Instead, some parts of the bearing are going to see much greater loads than other parts. And this graph is a first estimate of those loads and where they occur under some generic trajectory. So with a little bit more tooling, a little bit more development, we can use this kind of a simulation environment to simulate the normal operations of an excavator, and from that we can build out the expected bearing loads and understand if we should choose a different bearing, design it differently, or give some thought to how it may fail. Of course, we have the ability to create user accounts and to return to prior work that we've done by logging in. Otherwise, this will hang around as long as your browser session does. And that is the Mechanomy Model Composer. Again, it was an alpha level project, very much alpha, but attempting to be an introduction to the Modelica modeling language, and to show engineers that you actually can get force information without solving systems by hand. You need to spend a little bit of time in Modelica, but Mechanomy is here trying to help you in that, and also trying to make libraries that make some of those things easier. So yeah, give it a look. Composer.mechanomy.com. And yeah, feel free to email me hi@mechanomy.com if you want to talk about this or anything else. Thank you.